Hello, friends. This is Jim with Science Talk. Well, here it is. Finally, the long-awaited uh, discussion on the Milankovitch cycles. So, what is the Milankovitch cycles? Well, the hypothesis is changes in Earth's orbit, its orientation in space, and tilt of its axis will influence climate. So, a little background. Milankovitch cycles describe the collective effects of changes in Earth's orbit on its climate over thousands of years. It is named for the Serbian geophysicist and astronomer Milutin Milankovitch. In the 1920s, he hypothesized that variations in eccentricity, axial tilt, and precession of the Earth's orbit resulted in cyclical variation in the solar radiation reaching the Earth, and that this orbital forcing strongly influenced climatic patterns on Earth. He did this in an attempt to understand why on Earth ice ages seem to happen on a cyclical manner. So, and we now know in the intervening basically almost century that thanks to cores taken from ice, rock, ocean sediments, and so on, we're able to study Earth's past climate. We can ascertain the isotopic fractionation from that, measure levels of CO2, construct past climates, past temperatures, and so forth. We look at tree rings, the fossilized pollen. There's a whole bunch of things that we look at. Now, does Milankovitch explain everything perfectly? No. And have more on that later. So there's still some stuff going on that Milankovitch does not quite account for, but it does account for a lot of it. So, what are some of these movements here that under consideration? Earth rotates on its axis. That's one. The Earth revolves around the sun. That's another one. These change over time due to gravitational interactions with other bodies, Sun, Saturn, and Jupiter being the big three. Keep in mind, this is extremely complex, but there are some dominant cycles. So, let's first talk about what's called the eccentricity. In other words, the shape of the orbit itself. Earth's orbit varies between nearly circular and mildly elliptical. In other words, eccentricity, the value of the eccentricity varies. When the orbit is more elongated, there is more variation in the distance between the Earth and the Sun, and thus in the amount of solar radiation Earth's surface receives at different times in the year. In addition, the rotational tilt of the Earth, what's termed as obliquity, changes slightly. A greater tilt makes the seasons more extreme. Finally, the direction of the fixed stars pointed to by the Earth's axis, geometric axis, changes, and that's called axial precession. Basically, the Earth is wobbling around space like a top. You spin a top, and as it starts to slow down, it starts wobbling. That's Earth. In addition, not only is the shape of the Earth's orbit changing between nearly circular and slightly elliptical, but the pattern of the elliptical orbit around the sun itself rotates, and that's called apsidal precession. The combined effect of proximity to the sun occurs during different astronomical seasons. So Milankovitch studied changes in these movements of the Earth, which alter the amount and location of solar radiation reaching the Earth, which is called solar forcing. Example would be radiative forcing. Milankovitch emphasized the changes experienced at 65 degrees north due to the great amount of land at that latitude. Land masses changed temperature more quickly than oceans. Specific heat, which I've discussed with you folks numerous times before. And let's face it, oceans, there's mixing of surface deep water, and also the soil has a lower volumetric heat capacity than water. So, the orbital shape, eccentricity. The Earth's orbit approximates an ellipse. Now, I'm going to read to you some descriptions, and I'm going to show you something that I crudely draw, so my apologies for that, but I think we'll get across the idea. Eccentricity is an actual measure, and it measures the departure of the ellipse from circularity. So the shape of the Earth's orbit varies between nearly circular with the lowest eccentricity of 0.000055, or 5.5 times 10 to the minus 5. And mildly is elliptical, the highest eccentricity of 0.068. Its geometric or logarithmic mean is 0.0019. Now, I don't know how many folks are aware. Most of you, I know, are aware of the arithmetic mean. I've got 7 items. I add them up, divide by 7. That's my mean, my average. Well, a geometric mean is, let's say I have these 7 items. I multiply them together, and then I take the 7th root. So, for example, let's start with something really simple. I have 2 values, 4 and another 4. What's the average? 4 plus 4 is 8, divided by 2 is 4. That's the arithmetic mean. Geometric mean, 4 times 4 is 16. I multiply 2 items, so I take the square root. Square root of 16 is 4. Another example, 4 plus 6, that's 10, divided by 2, 5. Arithmetic mean. Geometric mean, 4 times 6 is 24. Take the square root of that. Well, we know the square root of 25 is 5, so it's obviously going to be 4.9. So slightly less. But I think you get the idea. So if I add up 3 numbers, 4 plus 6 plus 8, that's going to give me 18. I divide it by 3, I get 6. If I do 4 times 6 is 24 times 8, that's 192. I then take the cube root of that. So, and by the way, so you get the idea. That's basically how geometric means work. So going back to the eccentricity, and so eccentricity measures how elliptical something is. Now that is something, if you wanted to see how that is done, you can consult a trigonometric textbook, or you can consult a Calculus 2 textbook that has a discussion on polar coordinates, however you wish to look at that. So the major component of these variations occurs within a period of 413,000 years, with the eccentricity variation of 0.012. Other components have 95,000 year and 125,000 year cycles, with a beat period of 400,000 years. When you combine these all together, they loosely combine into an approximately a 100,000 year cycle. So variation of minus 0.03 to positive 0.02. The present eccentricity is 0.017 and decreasing. Eccentricity varies primarily due to the gravitational pull of Jupiter and Saturn. However, the semi-major axis of the orbital ellipse remains unchanged, according to perturbation theory. Not going to get into that. That gets really crazy and complicated. However, what this does is it does allow us to compute the evolution of the orbit. In other words, we say that the semi-major axis is invariant. It doesn't change. The orbital period, the length of the sidereal year, is also invariant because, according to Kepler's third law, is determined by the semi-major axis. So let me jump out of here and pull up this crude drawing. So this is my attempt to freely draw a an ellipse using this this little crosshair thing here. This is an ellipse. This red circle is supposed to represent the geometric center of the ellipse. These two black X's, what have you, are the foci. Focus is the singular, are the foci of the ellipse. Now, a circle is a special case of an ellipse. This blue line that goes across from here to here, okay, that's the major axis. That's the major axis of the ellipse. Perpendicular to the major axis and going from one edge to the other edge, going through the geometric center, is the minor axis. And using these values, you can calculate all sorts of things about ellipses. Now, as the two foci move closer and closer together, close and where they start to converge on the geometric center, the shape of the ellipse itself becomes more and more circular. So if I stretch this out this way and that way, it's really going to be a very elongated ellipse. Moving closer together becomes more circular. So a circle is when the two foci precisely coincide and overlap exactly at the geometric center. Then we have a circle, right? The definition of a circle is all points equidistant from the central point. So the semi-major axis is basically half of one of these. Half is basically half the major axis. So we're looking from the geometric center outwards. And that changes invariant. So basically what's happening is as the Earth's orbit is changing the eccentricity, it's the minor axis that's moving about. Now the apsidal precession is the ellipse itself is rotating about. So the shape is going to be going like this, right? Like that. But as it's doing that, it's also rotating around as it's doing its accordion. That's what this talking about apsidal precession. Okay. So I just wanted to kind of give you some little features to bear in mind as we continue our discussion here. So, now, how does orbital shape affect temperature? When Earth's orbit becomes more eccentric, more elliptical, the semi-minor axis shortens, which is what I just said. Okay? Now, the semi-minor axis is, again, the distance from the geometric center along the minor axis to the edge of the ellipse. In other words, half of the minor axis. This increases the magnitude of seasonal changes. The relative increase in solar irradiation at closest approach to the sun, which is called perihelion, compared to irradiation at the furthest distance, aphelion, is slightly larger than 4 times the eccentricity. For Earth's current orbital eccentricity, incoming solar variation varies by about 6.8%, while the distance from the sun currently varies by only 3.4%, about 5.1 million kilometers. Perihelion presently occurs around January 3rd, while aphelion is around July 4th. Notice that they do not coincide with when winter and summer solstices, respectively, occur. Keep that point in mind. That comes into play when we talk about precession. When the orbit is at its most eccentric, the amount of solar radiation at perihelion will be about 23% more than at aphelion. And we have 6.8%, so basically a little more than 3 times as much. However, Earth's eccentricity is always so small that the variation in solar irradiation is a minor factor in seasonal climate variation when compared to the tilt of the axis, axial tilt, and compared to the relative ease of how heating the large land masses in the northern hemisphere. Okay, so What about the length of seasons? Now, the seasons are basically quadrants of the Earth's orbit that are indicated by the two solstices and the two equinoxes. Kepler's second law states that a body in orbit traces equal areas over equal times. Its orbital velocity is highest, fastest, around perihelion and lowest, slowest, around aphelion. Earth spends less time near perihelion and more time near aphelion. This means that the length of the seasons vary. As I just mentioned a moment ago, perihelion occurs about January 3rd. So the Earth's greater velocity shortens winter and autumn in the northern hemisphere. Let me repeat that again. Because perihelion occurs January 3rd in the northern hemisphere, the greater velocity shortens the length of winter and autumn in the northern hemisphere. Summer in the northern hemisphere is 4.66 days longer than winter, and spring is 2.9 days longer than autumn for the northern hemisphere because of the current timings of perihelion and aphelion. As precession happens, as when the changes in the Earth's tilt of the orbit of the axis, tilt of the axis. There is a tilt of the orbit. I'll get into that later. But as changes in tilt of the axis relative to where it's found in the ellipse will determine perihelion and aphelion, how much sunlight reaches the surface, the radiation, and determines the length of the seasons. Greater eccentricity increases the variation in Earth's orbital velocity. Makes sense. The more ellipse it is, the more drawn out. When you're at aphelion, you really slow down. If you have a circle, the orbital velocity is going to be a constant. But when Isaac Newton was asked, why don't planets travel in circles? Why do they travel in ellipses? Thanks to Kepler's work, Newton said, I'll get back to you on that one. He goes home and invents calculus. Seriously, that's what happened. He invented calculus to answer a question why planets travel in ellipses. Now, currently, Earth's orbit is becoming less eccentric, meaning more circular, so this is going to make the seasons more similar in length. So think about it. If in the summer, northern hemisphere is almost 5 days longer than winter, but now the season is going to be more similar in length, that means summer is going to shorten down and winter is going to lengthen up. Now let's talk about the tilt of the axis, or obliquity. The angle of the Earth's axial tilt with respect to the orbital plane. Now, the obliquity is called the ecliptic. The orbital plane is called the ecliptic. This is the plane in which the sun and the 8 planets rotate around the sun. That's called the ecliptic. Okay? If the Earth, when we have the cloud of dust, and dust settles out, starts to coalesce, it starts to spin. Now, normally, this would spin perpendicular or normal to the ecliptic. But then something happened, something smashed into Earth and knocked it over. Uranus has the most amazing obliquity. It's like 98 degrees knocked over. It's literally like a marble rolling through space. Okay, that happened to Uranus. So something hit Earth. So now it hit Earth and the Earth tilted. So now the axis tilts between 22.1 degrees and 24.5 degrees over a cycle of approximately 41,000 years. The current tilt is 23.44 degrees, approximately halfway between the two extremes. The tilt last reached its maximum in 8,700 before current era, BCE. It is now in a decreasing phase of its cycle and will reach its minimum around the year 11,800 current era. This is important. Increased tilt increases the amplitude of the seasonal cycle in insolation, that's incoming heat from the sun, providing more solar radiation in each hemisphere's summer and less in winter. However, these effects are not uniform everywhere on the Earth's surface. Increased tilt increases the total annual solar radiation at higher latitudes, decreases the total closer to the equator. But because of more heat being received at higher latitudes, it warms up the higher latitude. So if you have ice, it tends to melt. As the axis decreases, the obliquity decreases, getting approacher to the 22 degrees mark, less heat intensity reaches the higher latitude, the ice is less likely to melt. So you have a buildup, a potential buildup of ice. So what's happening right now? The trend is decreasing tilt. Which leads to an overall cooling trend. Now, it may lead to warmer winters and colder summers. Now, warmer winters means that, well, instead of saying an average temperature of 10 degrees, it might be an average temperature of 15 degrees, still below freezing. Right? Colder summers, there's that not melting the ice bit. Because most of the planet's snow and ice lies at high latitude, decreasing tilt may encourage the onset of an ice age for two reasons. Less overall summer insolation, less insolation at higher latitude, which means that with less insolation, melting the previous winter's snow and ice is less likely to happen. So, basically, the Earth becoming more circular, which means winter will lengthen. The axis is becoming less tilted, which means less of melting of snow and ice and overall cooling of the planet. Right now, according to Milankovitch, Earth should be entering a cooling down stage. And what's happening? The planet is warming. You've heard me say before in other videos that Milankovitch predicts Earth should be cooling down, but we're warming up, which actually makes it easier for us to tease out the signals. Okay. I'm doing all the discussions first and then go through the slides I have here for you. So axial precession. Axial precession is the trend in the direction of the Earth's axis of rotation relative to the fixed stars with a period of about 25,771, 26,000 years. In other words, it's the wobble on its axis. This motion means that eventually Polaris will no longer be the North Pole star. It is caused, axial precession, by the tidal forces exerted by the sun and the moon on the solid Earth, land masses, not the oceans, and both contribute roughly equally to this effect. Currently, perihelion occurs during the southern hemisphere's summer. This means that solar radiation due to, one, the axial tilt inclining the southern hemisphere towards the sun, and two, the Earth's proximity to the sun, both reach maximum during the summer and both reach minimum during the winter. This is for the southern hemisphere. Their effects on heating are additive, meaning that seasonal variation in irradiation of the southern hemisphere is more extreme. In the northern hemisphere, these two factors reach maximum at opposite times of the year. The north is tilted toward the sun when Earth is furthest from the sun. The two effects work in opposite directions, resulting in less extreme variations in insolation. In about 13,000 years, the North Pole will be tilted toward the sun when Earth is at perihelion. Axial tilt and orbital eccentricity will both contribute to a maximum increase in solar radiation during the northern hemisphere summer. Axial precession will promote more extreme variation in irradiation of the northern hemisphere and less extreme variation in the south. And where do most people live? When Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, axial tilt will not be aligned with or against eccentricity. Let's now consider apsidal precession. This is the whole motion of the ellipse itself rotating about. And by the way, when I showed you that my crude diagram of the ellipse, the sun is located at one of the two foci. The sun is not at the geometric center of the ellipse. If that were the case, then there would be 2 aphelions and 2 perihelions occurring in Earth's orbit every year. The sun is located at one of the foci, and therefore we get the 1 perihelion and the 1 aphelion. So back to apsidal precession. The orbital ellipse itself precesses in space. That's what apsidal precession is about. Now, Milankovitch was unaware of this, so he did not factor this in. This is information we've been finding out in the last few decades. Now, it's an irregular manner, which it does thanks to the orbital tuggings of Jupiter and Saturn, and the cycle approximately every 112,000 years, and that's relative to the fixed stars. Apsidal precession occurs in the plane of the ecliptic and alters the orientation of the Earth's orbit relative to the ecliptic. Apsidal precession combines with the 26,000-year cycle of axial precession to vary the position in the year that the Earth reaches perihelion. Apsidal precession shortens the axial precession period to 23,000 years on average. As the orientation of Earth's orbit changes, each season will gradually start earlier in the year. Precession means Earth's non-uniform motion will affect different seasons. Winter, for instance, will be in a different section of the orbit. When the Earth's apsides are aligned with the equinoxes, the length of spring and summer combined will equal that of autumn and winter. When they are aligned with the solstices, the difference in the length of the seasons will be greatest. Finally, we have orbital inclination, which is the inclination of Earth's orbit drifts up and down relative to its present orbit. In other words, it isn't flat, but there's a little bit of a tilt, and that goes up and down. This three-dimensional movement is known as precession of the ecliptic or planetary precession. And this does not really factor in too much, but it's there. So I will get back to the problems with Milankovitch's hypothesis towards the end of this talk. Let's go through the slides here. Okay, so here's Earth's orbit. Now here's the basically the eccentricity. Now these drawings are exaggerated for illustrative purposes, right? Remember, the changes in eccentricity goes from 5.5 to the minus 5 to about 0.06, right? So this is again just drawn to show that it goes from nearly circular to a bit of an ellipse, and that's an approximately 100,000 year cycle. This is obliquity. Okay, here is the plane of the ecliptic, this horizontal dashed line that we see here. Okay, this is the vertical dashed line is the normal to the plane of the ecliptic. Normal means perpendicular. You will see words orthogonal, normal, perpendicular all mean the same thing. Where it intersect, it forms 90 degrees. So the red that we see here is about 22.2 degrees or 22.1. The green is our current position, about 23.5, and the blue is 24.5. So from 22 to 24.5 is approximately the range in how the tilt of the Earth's axis varies. So when it tilts furthest over the blue axis, if you will, that's when the northern latitudes receive more sun energy, which is more likely to melt any ice buildup, and so forth. When it gets to the red axis, about 22 degrees, it's less likely to do that. Currently, our trend is going towards the smaller tilt. So this is just another, about a 41,000 year cycle, normal to the ecliptic, and so on. Again, just to show an exaggeration in the direction of how the tilt will affect incoming heat energy. So, this is a little summation of the three major components of the Milankovitch cycle. Okay? Eccentricity, Earth encounters more variation in the energy that it receives from the sun when the Earth's orbit is elongated than it does when it's more circular. And you can see, when you're out here, you're going to get less energy than when you're like here or here. Whereas if you're more on a circular orbit, you're going to pretty much receive about average equal energy. This is the showing the tilt of the axis, between 22 and 24.5 degrees or so. But Earth is wobbling like a top. And this, what we see here, this little, that's called the circle of precession. So precession, a gradual change or wobble in the orientation of the Earth's axis affects relations between Earth's tilt and eccentricity. Right? Going back to obliquity, the tilt of the Earth's axis, right? The greater the tilt angle is, the more solar energy the poles receive. And again, this is showing eccentricity, aphelion, perihelion. This is putting the sun at the geometric center, which is not accurate, but I know why they did it for this reason here, because they had the circular orbit as well. But keep in mind, the sun is going to be at one of the foci. So again, showing obliquity and the precession. And, this is like showing, this is indicating it's spinning, but then the top is wobbling, and that's what Earth is doing. It's wobbling back and forth, okay? And so it basically varies between Polaris and Vega being the North Stars, and then back with some others in between. I think Thebes, I'm not sure if I'm remembering that correctly, but I think Thebes is one of those other stars in between Vega and Polaris that becomes a North Star. I do remember reading about a situation when looking at archaeologists trying to understand the orientation of the pyramids in Egypt. Couldn't figure out why they were oriented the way they were until they figured out, at the time when they were building the things, the Thebes, I think that's the star's name, was the North Star. And once they took that into account, then the direction or the facing of the pyramids all kind of made sense. But that's what precession is. The Earth is wobbling on its axis back and forth. And as it wobbles, it changes which star it points to as the North Star. That in turn will affect where it is in its orbit around the sun and how much energy reaches the surface. So again, this is done for illustrative purposes here. The blue solid curve is most eccentric. The green dash is least eccentric. To see the eccentricity, that has 100,000, 400,000, 13-year cycle. The tilt is about 41,000 years back and forth. It goes from here to saying 21.5. It's more like 22.1 to 24.5. It's currently at 23.5, and it's going back and forth. We're moving towards the 22. And the precession, there's some adjustments, but basically it's a little incorrect. It should be about 26,000 year cycle, 21,000 years, what have you. It's in the 20,000 year cycle. It varies. Those are average values. And again, this is called the circle of precession. So this is again a review, same thing as the previous slide, with just some little explanations. And you can, when you're viewing this, you can always pause the video and study the figures at your leisure. Okay, like a spinning top, Earth's axis of rotation wobbles. So the North Pole describes a circle in space. That's that circle of precession. The wobble of the Earth's axis causes the precession of the equinoxes. Now, and as I'll show you later, it slides around in the orbit. The positions of the equinox and solstices shift slowly around the Earth's ecliptical orbit, completing one full cycle about every 22,000 years, right? You see different calculations. Precession changes the time at which the Earth reaches its perihelion, serving either to amplify or reduce climatic seasonality. So we're looking at this from the top. Now keep in mind, okay, I have another slide that will show this better, but these quadrants represent, like, for example, that this would be an equinox, that would be a solstice, another equinox, another solstice, where the dashed lines reach the ellipse. Those define the season and basically the length of the seasons. North Pole tilted away from the sun equals northern winter. And right now, this is happening at perihelion. This is perihelion. Aphelion is at the other end. 5,500 years ago, perihelion occurred during the northern spring. So going back to the very first indicator here, seasonality reduced in the northern hemisphere. When the perihelion occurs during the northern spring, moderate seasonality in the northern hemisphere. When perihelion occurs during the northern summer, right, this is perihelion during the northern winter. Now we get the northern summer. We get seasonality increase in the northern hemisphere, and it's by a considerable amount. So this is what I consider really the most important slide, and what I think best explains all of what's going on here. And again, you can just pause this and stare at it. We're going to start here at the top. I'm going to go clockwise. Okay. Right now, this is at the very top is the current condition. If you look at this, there's a red arrow. The red arrow is the direction that the North Pole is pointing. Okay. Now, it's not aimed directly at the sun, obviously, but we're talking about the tilt of the axis. Right now, it's 23.5 degrees. Well, what we're saying is, when you see the red arrow pointing down, that means the axis in the northern hemisphere is tilted at the sun. At the summer, at the winter solstice, so this is at the summer solstice, at the winter solstice, it's tilted away. And here at the two equinoxes, it's basically parallel, if you will. It's not tilted directly at it or directly away from it. It's the in-between point. And that's basically at the equinoxes when you approximately get most latitudes will get equal amounts of daylight and darkness. Don't forget, this also affects, the tilt of the axis will affect, at different latitudes, how much daylight, how much darkness you get every day. And the Arctic Circle is defined as that latitude, and we got a similar one for Antarctic Circle, but the Arctic Circle is defined as that latitude where on winter solstice, the sun does not rise above the horizon at all. And on summer solstice, the sun does not set below the horizon at all. That's the definition of the Arctic, of the Arctic Circle. As the tilt of the sun changes, or the tilt of the Earth's axis changes towards the sun, the latitude at which the Arctic Circle will also change. The greater the tilt, the further south the latitude will move. The less the tilt, the further north it will move. And of course, that ties into how much radiation the latitudes recede, as well as the concentration of the radiation at those latitudes. That little thing here, the town of Circle here in Alaska was so named because when people settled there, they thought they were at the Arctic Circle because, hey, the sun shone exactly, it didn't set at all on summer solstice. Well, the town of Circle is actually on the Yukon River, and it's a little below the Arctic Circle. People forgot to take into account the bending of the light rays through the Earth's atmosphere. Be that as it may. But so when we're looking at this, and again, so we see the equinoxes, winter solstice, we can see the definition of the the seasons being defined: spring, winter, fall, summer. Okay. So this is the current condition. Summer solstice in the northern hemisphere, right? We're looking at that. This is all considering, right? Northern hemisphere is pointed at the sun, and it's at aphelion, which means the southern hemisphere, that's their winter. Southern hemisphere is pointed, the axis is pointed away from the sun. They're further from the sun, really less energy, which is why Antarctica is one of the reasons why Antarctica is really snottily cold at that time of year. In the winter solstice, in the northern hemisphere, the axis is tilted away. In the southern hemisphere, it's tilted towards. They get a little more heat in their summertime. But in the northern hemisphere, it's not as cold as it could be. Now, looking at precession direction, the wobble of the Earth, 5,000 years from now, look what's happening here now. Summer solstice occurs not at aphelion or perihelion, right? Remember, this is all at the top there is aphelion, and at the bottom is perihelion. So summer solstice, the axis of the northern hemisphere is pointed at the sun, and then winter solstice, it's pointing the northern hemisphere away from the sun. But the solstices are not occurring at either ap or perihelion. And again, the indicated seasons are for the northern hemisphere. Go further along to Earth's orbit 10,000 years from now, and now we see that at perihelion in the northern hemisphere, the tilt of the axis is directed at the sun, and then at aphelion, winter solstice for the northern hemisphere is away from the sun. Now it's going to get a lot colder and a lot hotter, respectively. And again, we still have, and also notice how, right, summer, spring, winter, fall. Right? This is summer, spring, winter, fall. You can see how the solstices and the equinoxes themselves are rotating around. That's the idea of precession. The timing is rotating on the elliptical orbit of the Earth. Now, keep in mind, the Earth's orbit, as it's doing this, it's going to be going more circular, less circular, more circular, less circular. In fact, approximately there's about 4 of these for every major eccentricity cycle going on. And then again, now finally, when we get to 15,000 years from now or 5,000 years ago, right, and we have this situation where the solstice for the summertime, again, is not occurring at ap or perihelion. So basically, we're alternating between the solstices being at either ap or perihelion or not being at ap or perihelion. And where it is changes how much radiation reaches the surface of the Earth from the sun, which then affects heating, which then affects weather, climate, and so forth. So, yeah, I'll just, you can always pause this and just really study, but this is a really good diagram explaining this aspect. So I'll continue on here. Now we get some signals here. Precession. Okay, this is basically a cycle here. And we have down here the stages of glaciation, and you can see the cyclical nature of it. At the top end is hot, okay, and we're looking at the solar forcing at 65 degrees north latitude. The present latitude for the Arctic Circle is, I think, 66 degrees and some 10 minutes. It's around 66 degrees now. So we're pretty much almost at the latitude of the Arctic Circle. Eccentricity, okay, the 9,525, 400,000 year kilocycle. Okay, so here's 400,000 years. So we start at this point here, we come to this point here, that's approximately 400,000 years. Okay, each dashed line, vertical dashed line, represents 100,000 years. Okay, so if you look from here to here, that's about the 95 that they're referencing here. But if you go from here, and so you have a low peak and a high peak, and then not so low peak, that's about 125,000 years. Okay. But here's that 100,000 years that they keep talking about. You can see from here to here, here to here. So you can see looking on here, you can see the approximate 100,000 year cycle, the general cycle that they talk about. The obliquity, 41,000 year, okay? Start from here, go to there, right? That's about 41,000 here. Go from here, go to here, it's another 41,000. So we're at 82, and you can see it's a little bit more to get to 100,000. So from here to here, basically count one peak and one trough, and then come to a line that's even with the initial starting point, and that's about your 41,000 year. And you can see, just look approximately. Think of this as like a sine wave, think of this like a cosine wave. But from here to here, if you count up here, you can count almost 2 cycles, right? Approximately. If I took 2019, I multiplied it by 2, I get 38. So you can see that for a precession, you get approximately 2 cycles for one cycle of obliquity. Obliquity is the tilt of the axis. Precession is the wobbling, which then changes the timing of the seasons and the location of the solstices in reference to Heri and aphelion, etc. Things we just discussed in this prior slide. Now, if you look at this solar forcing, you see how we reach the high peaks when, let's just grab this one right here because it's on a dashed line. Right? We can see how that correlates to most likely when the northern hemisphere at summer solstice is located at perihelion. Also, you see right here on the obliquity, the higher it is, the greater the tilt of the axis. So down here is about 22.1 degrees. This is 24.5 degrees. So solar forcing, you can see it as high. It's high on the greatest tilt, as well as when the northern hemisphere is tilted towards the sun at summer solstice at perihelion. And the peaks are going to change. This is when it's really cold, and you can see that it's down here as well. Now, when it's hot, right now I picked this first dash line just because it's easy to see. We can see that, look where these peaks are. You see how these peaks are kind of lining up with the peaks of solar forcing, the obliquity, and the precession. Of course, the solar forcing is a measure due to the tilt of the axis, where the Earth is in its orbit, how much eccentric the orbit is, so we can measure that. So, studying this graph carefully, we can see that greater axial tilt, the position of, you can actually deduce when the northern hemisphere is at summer solstice, whether it's aphelion, perihelion, or one of the other locations. and therefore how that drives the amount of heat that reaches the surface. The more, so eccentricity values here. Up here is more eccentric, down here is more circular. So again, we're seeing where it's more elliptical. It must be where in the obliquity, the precession, that it is lining up with the perihelion as well. So, and hey, going back to isotopic fractionation, right? We would see how this is cyclical. Is our del 18O fractionation. So now we're looking at basically, this is marl. So we're looking at calcium carbonate and 4 amps from the sediment. Remember the discussion I did on isotopic fractionation. The more positive the del 18O is in the 4 amp indicates a cooler period in Earth's history or glaciation. More positive, right? Minus 2.4 is more positive than minus 3.2. So this is cooler, this is warmer. Interglacial glaciation. We see it right there. So let's look at the natural factors influencing Earth's climate. Extraterrestrial solar output. Sun does vary in its output. The Earth-Sun geometry, relative positioning to each other. Interstellar dust could do some light scattering, energy scattering. Excuse me. Internally, volcanic eruption, throw a bunch of stuff up in the atmosphere, could cool things down. Mountain building could change the direction of winds and thus precipitation patterns. Continental drift, then of course atmospheric chemistry. Continental drift, plate tectonics, mountain building, continental drift. These are two of the major things where the Milankovitch hypothesis comes up a little short on, because Milankovitch does not take that into account. Now, he was doing his work in the 1920s. Alfred Wegener presented his idea of, the crustal plates, saying, they were all together and they moved about. Not, like 10, 15 years earlier, and Wegener was basically ridiculed. He said, solid Earth, how can solid Earth move around? It wasn't until the 1970s, and Milankovitch was long gone from this world by then, 1970, when we started getting more bathymetric data, and we saw the mid-oceanic ridges, and we started seeing the sea floor spreading, that we came up with the mechanisms for plate tectonics, and then you realize that the plates do move around. The other thing that Milankovitch didn't take into account was this guy right here. That little thing connecting North and South America, the Isthmus of Panama. When that formed, cutting off water flow from Pacific to the Atlantic side, that really changed Earth climate. And part of continental drift is Antarctica down there. So, Milankovitch cycles also influence climate. That's kind of been the point of this discussion. Periodic change orbits around the sun alters the way solar radiation is distributed over Earth. All these cycles talking about eccentricity, obliquity, precession. The thing is, it changes how sun energy reaches the Earth. That's all these factors change how much energy reaches the Earth at every latitude. These cycles modify patterns of atmospheric heating, triggering climate variation, glaciation, cold temperatures, ice sheets, right? All these things here. Earth's most elliptical orbit, farthest from the sun, favors glaciation. Couple that with where it is in the precession of the equinoxes and solstices, what the tilt of the axis is, and so forth, right? Because going back to here, over 100,000 year cycle of the eccentricity, we have a whole bunch of obliquity cycles, a whole bunch of precession cycles. And then if you go at the 400,000 year cycle, you really have a whole pile more in between. So, complicated system. So that statement, Davis glaciation, is a general one. It's true overall, but the extent of glaciation depends on exactly the wobble of the Earth, the tilt of the axis, how eccentric the orbit is, and where it's going on. Not to mention that this whole ellipse itself is rotating about thanks to the influence of Saturn and Jupiter. So, on this side, we have glacial conditions. On the right side, we have interglacial conditions. So, insolation is at a minimum. We have increased albedo. Albedo is the reflection of sun energy off ice surfaces, white surfaces, right? It's hot in summertime. Do you put on a black t-shirt? No, you put on a white t-shirt. But the black t-shirt will absorb energy and make you feel really hot. Well, if you have a pile of ice, like Antarctica, there you go. It's going to reflect a lot of energy back to space. Also, we have lower sea level because, remember I discussed in the isotopic fractionation video. The water leaves the ocean, comes down the snow, packs down as ice. Sea levels drop. The thermohaline circulation is cut off. Thermo for temperature, haline for salt. That's deep water formation. That's the Atlantic meridional overturn circulation as an example. There's also one that comes off of Antarctica. Decrease in SST, sea surface temperature. Insolation is maximum. The albedo is reduced. Okay. The thermohaline circulation is on. In other words, it's operational. Biomass, CO2, precipitation, isostatic depression. What is meant by isostatic depression? You put a big pile of ice on the land, the weight of the ice squeezes the crust and actually pushes the crust down. As the ice melts, that pressure is being lessened, so then the ground, the landmass itself, starts to rise. That's isostatic rebound. So in glaciation periods, there's isostatic depression. Interglacial periods, as the ice melts, is isostatic rebound. So that's what we see going on with that. Now, here's the insolation at 65 degrees summer latitude. This is kind of, the green is the obliquity contribution. And if you look, the obliquity, right, that's the tilt of the axis. So that's the green. The higher the green is, right, the highest is 24.5 degrees. That's about here. The lowest is 22.1 degrees or so. And you can see that when the axis is least tilted is when you have, overall, generally speaking, cooler situations, less energy at the 65 degree. This is measured in watts per square meter, sometimes called joules. The blue dot here, just slightly off of zero, is current conditions. But it doesn't track perfectly, but it tracks nearly nicely. It does tie in the overall trend. What are the other differences? Precession, eccentricity. They'll slightly vary that. But it does track quite closely. So, a little summation of the Milankovitch cycle. Earth's climate undergoes 120,000-year cycles of ice ages broken by short warm periods called interglacials. The cycle is driven by a Milankovitch cycle. Long-term changes in Earth's orbit trigger an initial warming, which warms the ocean and melts ice sheets. This releases CO2. The extra CO2 causes further warming, leading to interglacials, ending the ice ages. Past 12,000 years have been interglacial. The current trend of the Milankovitch cycle is a gradual cooling. What are we doing? We're warming the planet. Milankovitch predicts we should be cooling down, but we're warming the planet. But as you have heard me discuss with you before, I am of the opinion that this warming will bring us into an ice age. The question becomes how much thermal inertia energy is in the system to offset it, forestall it, what have you. And what happened? We have evidence that when the thermohaline shuts down, the AMOC, when that shuts down, Earth cools down. Right now, we are measuring the deep water formation as slowing down. Because the conveyor belt is a heat distribution mechanism for the planet. You shut that down, you're going to get greater gradients in temperature, such that you get the ice age from mid latitudes to high latitudes and hot tropics in between. Although sometimes the tropics may not be all that hot, as we have evidence for in the past. But we do have some evidence for previous situations where like a little ice age, where the thermohaline circulation was off. So does Milankovitch hypothesis hold up? Excuse me. It explains a lot of the variation, but not all. It's incomplete. Its overall R-squared value is approximately 0.73. There are other factors that influence climate, including plate tectonics, changes in the solar output itself, in addition to the Earth's orientation, changes in ocean circulation, surface and deep water flows, that I just alluded to, anthropogenic effects, which I just alluded to, for example, climate change. The main thing that people need to remember is that in Earth's deep past, it was a hell of a lot hotter planet with higher CO2 levels, and I just did a video on that. But when Antarctica got to its current position, literally at the bottom of the planet, that's when, and the snow started building up, becoming ice, that's when Earth really dramatically cooled down. Then you add the Isthmus of Panama arising, cutting off flow between the Pacific and Atlantic Oceans, the communications there, creating the Gulf Stream, which brings warm tropical waters to higher latitudes, gives off its heat, it comes down as snow. That also helped trigger ice ages. So, in the deep past, when Earth was considerably hotter, would humans have been able to survive? Short answer, no. And too hot. There's actually a hypothesis among anthropological circles that the reason for the rise of human civilization is because the arising of the Gulf Stream. I haven't studied their hypothesis too much to make a comment on it, but I know it's out there. So anyway, that's the end of that one. So I hope you found this informative, and hope you can see how changes in the Earth's orbit, its tilt, the wobble of its axis, how this will induce changes in how much solar energy is received, and thus therefore affecting the climate. So now to the climate deniers, when they point to things like this, you can tell them, we can tease out the signals. The fact that Milankovitch only gives us an R-squared 0.73 and not higher tells us there are other things going on. And the other things going on are the plate tectonics, the anthropogenic effects. As well as we use isotope fractionation to identify the sources of the CO2 molecule, and all the other studies being done, measuring the warming up of the oceans, etc., etc. All the videos I have done discussing various things. So this is not to say that Milankovitch is not happening. It is. But when you look at the time scales involving human civilization, in the short term, what we're doing to the planet will harm civilization. In fact, threatening civilization. Earth will be fine. Earth will continue doing its thing, eccentricity changing, it's wobbling, and the tilt going back and forth. Earth will keep doing its thing for the next 5 billion years or so until the sun starts to expand, and eventually the sun will expand such that it will expand past the orbit of Mars, which means wearing away, and our Earth will be burnt to a cinder at that point. But in 5 billion years from now, there's no way on Earth humans will still be around. In fact, the way we're going right now, we are threatening our survival. Earth will be fine after humans are extinct. All our structures will be reclaimed by nature. The whatever sixth extinction that's been initiated by humans will reach its conclusion, and then there'll be more evolution, more new animal forms will happen, etc., etc. And and planet Earth might actually breathe a sigh of relief. They'll finally got rid of those crazy people, those crazy species. So anyway, there's my Milankovitch presentation. Hope you like it. Hope you found it informative and interesting. Thank you for your time. Hey folks, this is Jim here reminding you to subscribe to this channel, to share my videos, tell others of the work that I do here. I also ask that if you are not already a patron at Patreon, to please consider becoming a patron at Patreon. You can find the information in the description box below the video. I'm asking you to help support the work that I do. I do not take any money from corporations or from any other sources, so the information I share with you is the actual science as it comes out of the peer-reviewed journals. So there is no BS, there's no propaganda, there's no agenda. It's just I present the science and I explain to you what it means, or at least my interpretations of it, based on my own experience as a scientist. I want this channel to grow. I consider, while I discuss many different topics here, you notice I do focus a lot on climate issues. I consider climate change to be the most pressing issue facing humanity today. Thus, I consider it important to disseminate this information to a wider and wider, more and more people. And I need your help to do this. So, yes, please subscribe. Please tell others of the work that I do here. Please share my videos on social media platforms, with your social media groups, what have you. We need to get this information out there. So for those of you who are supporting me on Patreon, I thank you greatly for your support and continued support. It does mean a lot to me. So together we can get this information to more and more people. Thank you. Thank you for your support.